Geometry lesson 6-1. We're going to start talking about polygons today and some of the relationships and specifications about those polygons. To begin with, a polygon has to have at least 3 sides, which means a triangle is the smallest number of sides that we can have for a polygon. A square can be a polygon, a rectangle can be a polygon because they both have 4 sides. They don't always have to have the exact same number or the exact same value of angles or sides. Each one of those sides must also intersect 2 other sides. Alright? So if you're thinking about an actual shape and you look at a triangle, this side is intersecting 2 other sides. Right? It has to have that in order for it to be a polygon. The lines must be straight, no curves, which means a circle is not a polygon. So we're talking about at least a minimum of 3 straight lines making those sides that intersect 2 other sides. So no curves. The vertex is the point where the sides come together. So one point where they come together is known as a vertex. The plural form, what we would call all of them, is known as a vertice. So here I just have a couple shapes, a pentagon and a hexagon, and I'm pointing at all the vertices around here. So here's one vertice, there's another. This one has 6 vertices, this one has 5 vertices. The number of vertices is the same as the number of sides. Okay? Each endpoint where they come together. The corners, for lack of a better term. We also have some that are known as convex polygons. Now, there's a way of telling whether you have convex or another form that I'll speak of in a moment. If I draw a dot here and I draw a dot here, those are both inside this particular polygon. It would be impossible, no matter where I put these dots, to connect them with a straight line in such a way that it would leave the shape. In other words, no matter where I put these dots, even if I move it here and move it over there, or like this, it's not going to matter. No matter what, I will not leave the shape in order to do that. However, if I have a concave or non-convex type of shape, polygon, it is possible for me to draw 2 dots in a location that when connected, the line leaves the shape. Now someone might say, yeah, but you don't have to put the dots there. You could put it down here and it wouldn't leave the shape. That's true. There are some locations on here where I could put 2 dots and my line would not leave the shape. There is nowhere that I can put 2 dots on here where it would leave the shape. And there are some places down here where it could. The fact that it could leave the shape means that it is not going to be considered convex. I think of concave as it looks like something is indented or fell in. If our roof caved in, it would be coming inward concave. Alright, so that's how we kind of refer to it. But that's the technical way of deciding whether or not it's concave. Can you draw 2 points and connect them with a straight line, and would your line ever leave the shape you're dealing with? If it does, then it's not considered convex. Regular polygons must have equilateral, or same side lengths, and equal angular, same angle measurements. You can have a regular pentagon. If it's a regular pentagon, then all 5 sides and all 5 angles are going to be exactly the same as each other. If you don't have that situation, then you're dealing with just a polygon, or just a pentagon. So in order for it to be regular, it must be the same. You can have equilateral triangles. That means all the sides are the same, and consequently all the angles are too. Or you can have an isosceles triangle. They're still triangles, they're still polygons, but if they have the same values, then they would be considered regular. The diagonal portion is important because it helps us learn a lot about the polygons themselves. Diagonals connect 2 non-consecutive sides at the vertices. So for example, if I were to pull up a square and I wanted to have its diagonal, there would be a diagonal and there would be considered a diagonal. Because I'm not going to go from here to here, because that's actually the side of the shape itself. So it can't be consecutive. I can't go from one vertice to another in a row. I have to skip a vertice in order to draw a diagonal. Right? Other shapes get a little bit more complicated. So with a pentagon, and I look at my diagonals, there's a diagonal, 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 and a diagonal. More diagonals. If we look at a hexagon, and I look at the diagonals, much more complicated. There's actually a pattern to them. This one had 2 diagonals. This one had 5 diagonals. And this one had 9 diagonals. As the number of sides increase, it goes up by 3, then it goes up by 4, and I'll bet you could guess the next one would go up by 5. So if I were to draw a 7-sided shape, heptagon, it would have 14 diagonals in it. Alright? We also use these, if I were to look at those shapes again, I can use these to determine how many total angles there should be within the shape itself. So here is one diagonal, only using one vertice now instead of all the vertices to create all of them. If you look at this, this forms 2 triangles. 180 degrees, 180 degrees means that all 4-sided shapes will total 360 degrees. This is 180, 180, 180, which means the grand total of all of them will be 540 degrees. 180, 180, 180, 180, 720 total degrees. And there's a connection here. If you look at the number of sides, this is a 4-sided shape, 5-sided shape, 6-sided shape. Look at how many diagonals or triangles there are. There's 2 less triangles. Take the number of sides and subtract 2, and that'll always give you the number of triangles. So number of sides minus 2 will equal number of triangles. And then if you want to know how many total degrees there are, it's the number of triangles times 180 equals the total degrees. And then if it's regular, if all the sides are the same and all the angles are the same, you can take the total degrees and divide by 4 or divide by 5, and it would tell you how much is in each one of those corners, each one of those vertices. So using that information, here we have a 4-sided shape. We're going to find the values, the measure of angle F, the measure of angle G, and the measure of angle H. Now G is the easiest because it has one arc here and one arc here. They have to be the same. So that means that G has to be 55 degrees. X and X are obviously the same. The fact that it's 4 sides means it's going to equal 360 total degrees within the shape. We just discussed that a moment ago. So 55 here and 55 here, you put all the angles together, it's going to have to make 360. So 110 plus 2x equals 360. Subtract 110. You end up with 2x equals 250. Divide by 2. And x is 125. 125 degrees. 125 degrees. The concept of being able to use the diagonals to determine the total number of degrees within a particular polygon is pretty valuable. These 2 formulas help you to do that.